In the last parts of last lecture, we are talking about the conditionally stable system. So I provide some additional lecture slide about the practical consideration of this conditionally stable system. Maybe probably you don't have this lecture slide, okay? But this will be included in the post-lecture slide. Okay, just focus on this, okay? Listen to me carefully. And this will be uploaded along with the lecture video. So this is the conditionally stable system. So conditionally stable system is stable now because it does not encircle this one, okay? So it crosses this minus real axis outside of this unit circle twice, okay? But this is stable according to the Nyquist stability criterion. But this is stable on the assumption that this gain is this. So this is originally stable system. But suppose somehow the feedback gain is reduced, that will be resulting in this, the shrinking of this. So everything, the shape will remain the same, but this loop gain will be just shrink like this. Okay, then this critical point is encircled, and this becomes unstable, right? So for this case, we cannot apply our simple criteria for the stability. We established a very simple result, but that cannot be applied here. It's something else, okay? But this becomes unstable, okay? So this is the typical characteristic of conditionally stable system. So to judge whether those system is conditionally stable, this polar plot travels. This is the first quadrant, second quadrant, third quadrant, fourth quadrant. It travels partially this second quadrant. Okay, then that is called conditionally stable system. Okay, so that is saying this is the same as the previous statement. In this statement, this magnitude of phase of loop gain falls below minus 180. So this is minus 180. It goes below that. It becomes more negative than this one. Then it should go this. It should enter this second quadrant. Okay. So there is the same thing. Or it falls below this before crossing the unit circle. Okay. So that means it goes into this second quadrant, enters and comes out altogether outside of this. That means the amplitude of this loop gain is larger than unity during this process. Okay. In terms of Bode plot, this is a 0 dB line. So 0 dB line is the frequency at which this polar plot crosses the unit circle. Okay. So in polar plot, the phase falls below this line. This line is minus 180 degree. So during this part, the polar plot is traveling in the second quadrant. Okay, and after that, it becomes 0 dB. So after traveling this region, after traveling part of the second quadrant, and it crosses the unit circle, and that means amplitude reduces to this one, 0 dB. Okay, so then maybe there is a pole here, 0 here. Then phase will be changed like this, and then at this point during this region, the phase is minus 180 degree, and at this region phase is minus 90, and at this point theoretically it is minus 135 if the corner frequency are widely separate. Okay, that is the assumption. Then this is true. Okay, so first criterion is this one, second one is this one, and there is another sign of this being conditionally stable. Before this loop gain crossover frequency, slope of this magnitude curve, it has some line segment with -3 slope. Okay, in this slope, this phase will be minus 270. So phase is approaching to here, to this. Okay, but it won't go that far, but it will falls below this minus 180 degree, and this trajectory will move into this second quadrant partially. Okay, so these three are same statement, and for all cases, this system becomes conditionally stable, and conditionally stable system, this is stable. Okay, originally stable, but becomes unstable with a reduced smaller feedback gain. Okay, so system is stable as long as the feedback gain is very large. Okay, so you may think this is okay because the feedback gain is, my feedback gain is always larger than something, then it stays stable. Okay, but that is your hope. Because of these characteristics, all right, this is the loop gain, polar product of originally conditionally system, trajectory of loop gain of conditionally stable system, and if gain becomes smaller as a feedback gain, I'm talking about the feedback gain, that will shrink and shrink. Okay, at this point, it passes this point, then the sustained oscillation will emerge, and if you further decrease, okay, this becomes unstable. Okay, there is, I'm sorry, I'm very sorry. Junk mail. Okay, understand this, right? So this was stable, but if the gain is reduced, it becomes unstable. Okay, but there is a situation, inevitable situation. This happens in practical application. All right. So suppose you have the amplifier in between in the feedback path. This is the gain characteristic amplifier. This is the input and output. And this amplifier, this is some amplifier, has this slope. Okay, this kind of slope is linear amplifier. If operating point is somewhere here, this slope is what? This slope is the gain, small signal gain. It's very large in this region, but operating point moves to this direction. If ideal linear amplifier, this curve extends this direction forever. But in all the practical amplifier, the amplifier will be eventually saturated for large input voltage in positive direction, in negative direction. So this is inevitable. This, okay. Then this slope is what? Slope is feedback gain is reduced. Slope is reduced, and slope becomes 0. That means feedback is terminated. Open loop operation. Okay. Same is true in this region. Originally, the operational region was here. This is your desired location, but somehow it goes this direction. Then gain, feedback gain, is reduced. That means this polar product got shrink, and it becomes unstable. Okay, this occurs when your amplifier saturate. Okay, this will occur frequently. Okay, during the startup process, maybe there is some protection mechanism like the soft start. Okay, assume there is no features of something like that. Then during the startup or large transient response, large step load change, step input change, the operating point will temporarily move to here, to there. Then the system becomes unstable. That is problem. Okay. Another one is some protective mode operation, maybe the current limiting operation or duty ratio is saturated. Okay, that means the feedback gain becomes 0. Then it shrinks forever and system becomes unstable. Okay, so this is a very bad situation. All right. Suppose you fabricate some motor which is very stable. Okay, this case, and you installed that in some spacecraft or airplane. Okay, during the flight, something happens, then it will move this by protective operation or some large transient response. Then system becomes unstable. Then the disaster will occur. Okay, so that is a very bad situation. So you should avoid this. So in some sense, this system is worse than unstable system. If a system is unstable, initially it becomes unstable, then you know the problem, you will fix problem. Okay. For this case, sometimes it looks okay. Okay. If you didn't check the details about this loop gain, you may think this system is acceptable, and during the practical application, it causes the catastrophic failure. Okay, and everything will breaks down, which is disaster. So to avoid that, you should avoid this. Okay, so this is the worst case scenario, and this is the worst case, all of them. Okay, so this is conditionally stable system, and during the design process of PWM converter, there are chances to come up with this situation. If the careful care is not exercised, okay? So you need to be very careful about this feature, all right? So easiest way is to avoid this situation. Before the loop gain does not have this kind of characteristic, -3 slope, okay? It's very bad, okay? This indicates there are good chance of being conditionally stable. All right, and marginally stable system. This is the one example. This is one example. This is the loop gain, Bode plot of the loop gain of maybe one badly designed PWM converter. So you take a look at this. Okay, when phase falls this 180 degree, it passes this 0 dB line. Okay, that means when phase is this one, this is 0, so there is a sustained oscillation going on. Okay, so system is unstable. Okay, and system is unstable means when loop gain is evaluated at this frequency, magnitude is 1, right? Phase is -180. That is a single number. What is that number? That number is -1. Okay, so this indicate at this frequency FC is loop gain crossover frequency, 0 dB crossover frequency. At that frequency, magnitude is 1, which is 0 dB. Phase is -180 degree. This is what? Number -1. Okay, so it becomes -1, right? So this is a loop gain at particular frequency of omega c, which is j 2 pi times fc. Fc here is 2k hertz. Okay, that it becomes -1. Okay, it becomes -1. Okay, so this is just the interpretation of this. This is a mathematical representation of this graph. Okay, then you move this around here. So this Tm evaluate at this particular frequency is -1. Then you move this, then 1 plus Tm evaluate at this frequency is 0. Okay, 1 plus Tm is what? Is the characteristic equation of feedback system. You know, this is a characteristic equation of a feedback system. So this is a characteristic equation. Characteristic equation of the system, and at particular frequency it becomes 0. This is what? Root of equation is called pole, system pole, closed pole, or eigenvalue. Okay, so eigenvalue or pole is located this one. This is what? On the imaginary axis. Okay, so then what will happen is here, This is the duplication of previous statement. This is the characteristic equation, and it satisfies this because of the loop gain characteristics. Then this is what? This is root of characteristic equation. So you have this positive one, then there should be a negative one. So root occurs in the complex conjugate form. That means in S-plane, assume this is S-plane, then there is one root here, J omega C, then there should be another root here, minus J omega C. Okay? Okay. Let me go through this. I forgot to mention this. This is what? This is Bode plot, and this is polar plot. Okay? The same thing. Okay? But this is, I use the same data, and I plot this in the polar plot format. So it starts from this, here, goes here, and it goes to the origin. Okay? And it passes this critical point. This frequency is, this is omega C is 2 pi times 2 times 10 to 3, because this is the same frequency. So stating this, at this frequency, phase becomes minus 180 and magnitude becomes 1. It's the same as this polar plot is passing through this critical point, minus 1, 0. It's the same information. Okay, with this information, we have this, and with this, you know, there is a one pole here, then there is a 2 pole on the imaginary axis, then the system is unstable, and it generates sustained oscillation at this frequency. Okay, that is the theory of classical theory, very basic theory of linear time invariant system. Okay, so this is a characteristic equation, and it's obvious. This is the root of characteristic equation called pole or eigenvalue. Then classical control theory says there is an oscillation at that frequency, at this frequency. This is the frequency of sinusoidal oscillation. So oscillation at this frequency will occur. So you are seeing this. There is oscillation. If this one is linear time invariant system, we have this smooth oscillation, but this is a PWM converter. So there is a ripple on the top of this sinusoidal oscillation, but this period or the frequency of oscillation, period of oscillation, this is the oscillation frequency, and the oscillation period is this one, 2 pi divided by omega C is this number, and this is expected to be 0.1 millisecond. So this length of period is very similar to 0.5 millisecond, not 0.1, but 0.5, right? This is a characteristic of critically stable system, marginally stable system, borderline between stability and instability. So frequency information is contained here, but magnitude information, you need some other theory. Okay, it's not covered here. Okay, and I won't go through that, but somehow this is determined, or you can control it. All right, so this magnitude of sinusoidal wave. In this fashion, you are making the sinusoidal oscillator, signal generator, without this. Okay, of course, the linear circuit does not have any ripple component, but we have ripple component. Ripple component is something else. Okay, you have ripple here. Is inherent characteristic of PWM converter. Okay, that's all about this marginally stable system. Okay, and okay, 5 more minutes. Okay, then we take a short break and we'll finish up the later part of this. Second one is another important concept is this gain margin and phase margin. Okay, so loop gain is complex quantity, so it has magnitude and it has phase. This is a complex number. So this polar plot is drawn in S domain, This is the real part, and this is imaginary part. Usually, okay, sigma j omega type notation. Okay, so this is the original system. System is stable because when phase falls to minus 180, so this passes the line segment to A, so this is stable. Okay, if we increase the feedback gain while maintaining the phase, if you increase the feedback gain while maintaining the phase characteristic constant, then this phase, this shape remains the same. It just expands out. Okay. If gain increase, then it will be increased. It will be increased. If increased this much, system becomes conditionally stable. If we increase further, the condition, the converter becomes unstable. So this is a direction of increase in gain, feedback gain. Okay. So eventually, any system, any stable system will become unstable if gain is increased. Okay, it's a problem. Okay, and conditionally stable system is originally stable, but if gain reduced sufficiently, then becomes unstable. So we have same problem, but they are not the same. They are very different. Okay, the maximum gain you can obtain is limited by design. Okay, in your amplifier design, feedback amplifier design or feedback controller design, maximum gain is limited. The usually gain cannot increase further than that. Okay, but this conditionally stable system situation is quite different. Okay, you fix the gain, but this gain always reduced during that period, some strange period. So conditionally stable system is very dangerous. But this stable system is not dangerous because the maximum gain is fixed by design. Okay, so there is no problem in terms of the gain increase. There is no chance to you increase gain above your desired limit. Okay, so anyway, this just increasing the gain is the same as stretching out loop gain plot. That is obvious. Okay, so let's consider this one. This one is originally stable because this passes line segment A, okay? And you introduce the phase delay in the loop, feedback loop, while fixing the gain. That means this radius may remain the same, but with additional phase, this will be rotate in clockwise direction. So you have this margin initially, but if you rotate this margin, or you add additional delay of this much, okay? So this is minus 1, 0, and this is unit circle. So unit circle is important, and this minus 1, 0 point is critical. Then it passes this, becomes marginally stable. If you further increase this, decrease this, or increase the phase delay beyond this level, then it passes this line segment B, C, and the system becomes unstable. Okay? So with this, we come up with the margin in the gain. How much you can increase the margin, the gain, while maintaining the stability. And from this plot, you can introduce the concept of phase margin while fixing the magnitude of feedback gain, how much phase delay you can introduce within the stable region. That is the margin. So this is related with the phase margin. This is related with gain margin. Okay. So very original reason for this is gain increase or phase delay increase eventually destabilize the system. So we should define some margin. Okay. All right. Let's take 3-minute break and we come back and we finish up maybe several pages, and that content is important because one of the problem is related with the gain margin and the phase margin. Okay? All right.